Well, hello class. I decided that I would put together a short video on sort of a long-form example problem for lateral torsional buckling. We have discussed this in class, but I thought I would just combine everything together we have learned into sort of one overarching video. So this isn't directly going to be presented in a class, but I just thought I would create a nice video example problem that I can post on the site and you can reference. Alright, so let me lay out the problem that I want to work through. So this is going to be a longer lateral torsional buckling problem. I just thought it'd be nice to combine everything we've seen together into one thing, including calculating CB values and everything else. So let's give this a shot, shall we? Okay, so here's the situation. This is going to be an analysis problem. And I have a beam with a 20 kip point load at the end. So this is actually going to be a cantilevered beam. So it is a 20 kip point load at the end. And this thing is 25 feet long. So 25 feet long. Basically, I'm going to go through the full lateral torsional buckling calculation, including calculating CB. In this example, I am not going to assume CB is equal to 1. That is a conservative assumption we can make, but often it is way too conservative. So I'm given that we have this beam here, and I'm also given what it is. So let's say I am given this here. Okay. Forgive me for the poor writing. I'm used to writing on my laptop. I'm working on my home desktop this evening with this tablet. But it's a bit of a late night lesson, but that's okay. And let me tell you about this beam. This is a W section, and it is a W21 by 73, and it is A992 steel. We're dealing with A992 steel, and I will say it is braced at the end of the cantilever. It is laterally braced at the end of the cantilever. At end of the cantilever. If you read on the notes on the CB calculation, if we did not assume this, then if it wasn't braced, then whenever we have a cantilever, the CB will be equal to 1.0. Okay, so the very first thing I'm going to do is I'm going to go to the first section in the steel manual, and again, this will be on this is going to be on page 1-20, and I'm just going to gather up a whole bunch of section properties that'll prove useful throughout my later calculations. So let me just write a few of these down. You should be able to find all of these fairly quickly in your steel manual. Just go to page 1-20 in the 14th edition, and you'll find and look at the section properties for a W21 by 73. So let me write down all the section properties. Now I don't know if I'll need all of these, but I just wanted to get them all in one place, so I didn't have to keep referencing back to this section of the code. And more importantly, one of my goals for this example was that I wanted to work through something without using any design aids. Oh, and I guess I suppose I should ask I should tell you what we're going to try to find. And we're going to find, well, this is just a very straightforward analysis problem. If W21 by 73 is adequate. So I'm find if the W21 by 73 is adequate for this load. Now it doesn't look like much at first. It's a 20 kip load. Like I said, it's 20,000 pounds. But what's really going to kill us is that this is a 25 foot long length. So that's going to be quite a bit. But let's write down a bunch of section properties first, and I'll reference these throughout the rest of the example problem. Alright, so just going to be doing a lot of writing. Well, let's see. We have the A, the D, the area, the cross-sectional area, the beam depth D, the thickness of the web TW, the width of the flange BF, the thickness of the flange TF, and that's it for this column. This is 21.5 inches squared. The depth of the beam is 21.2 inches. The thickness of the web is 0.455 inches. The width of the flange is going to be 8.30 inches. And the thickness of the flange is going to be 0.740 inches. Then I'll get my, you know what, I think below here I'll write my, some of my other constants that I'll use later. My RTS, this will be useful for a later calculation, is 2.19 inches. And we could calculate this ourselves, but conveniently it's already calculated for us. And our H0 is 20.5 inches. Then let's see what else. Our compact section criteria. So these are going to be used for lateral torsional buckling. And then our compact section criteria. Oh, let's see. I'm going to have BF over 2TF is already calculated for us, and this is 5.60. So this is the slenderness check, or the compactness check for the flange, or that limiting ratio anyway. And the H over the TW is going to be equal to 41.2. 41.2, and then a few other things. Well, let me say that the J is going to be 3.02 inches to the fourth, just of our torsional properties, and our CW, capital C subscript W, is 7,410 inches to the sixth power. And then from this, the only other things I need to have are my my various other properties, my various other section properties, my IX, my SX, my RX, and my ZX, so my strong axis and my weak axis properties, and IY, SY, so this is for the weak axis along the YY axis, my RY, and my ZY. Let's see, this is going to be 1,600 inches to the fourth. My SX is going to be 151 inches to the third. My RX is going to be 8.64 inches. And my ZX is going to be 172 inches to the third. Again, all of this is just coming straight from the table of properties. And then finally, my last section properties, IY is 70.6 inches to the fourth power. My SY is 17.0 inches to the third. My radius gyration in the weak axis is 1.81 inches. And my ZY is 26.6 inches to the third. Now, we won't actually be needing every single one of these, but you know what? In this particular example, I have to use so many of these section properties that I sometimes find it's more convenient just to write everything down, get it all down on my page, and then I don't have to worry about coming back to it in the steel manual. Alright, so the way I'm going to work through this is to go through a series of steps and label those. Alright, so let's talk about our first step. Well, the first step is to calculate our max moment. Oh, and I will mention that this is a P ultimate. I should have also mentioned that. This is already a factored point load, so we don't need to do any kind of load combination on that. And so the first thing then is to calculate the max moment. Max moment, we need to actually have something to compare to. And this one is just statics. This is trivial. All you have to do is we go, okay, well, I took statics class, so I know how to calculate this. M ultimate is simply 20 kips times a moment arm of 25 feet. If you don't know how to do this, please go take statics again. And this will be 500 kip feet. 500 kip feet. So this is our M ultimate. We need to make sure that this beam can withstand an ultimate moment of 500 kip feet applied to it. Alright, so our next step is actually going to be to calculate or to check the compact section criteria. Now we could just go and look at the table and say, oh, it doesn't have a note on it, but you know what? I like to actually check this. I like to. This is a good habit to be in, because again, this is always for the notes on the table, on the first table there, on the section properties table. Sorry, those are going to deal with 50 KSI steel. They're going to deal with your normal, typical ruled sections. You'll often have things that aren't so neat and simple. So I do like to get in the habit of actually checking directly the compact section criteria, and I will be asking you to do this on the exam. So check compact section criteria. Check compact section criteria. And so let's see. Well, let's look at the flange first. Well, I can go to table B 4.1b, and as we've seen before in class, the limiting ratio for compact, for the limit for compact flanges is going to be, well, in a strong axis flexure, of course, 0.3 square root of E over Fy. And this is going to be 0.38 times the square root of 29,000 KSI over our yield strength of 50 KSI. And this comes to 9.15. And from our previous slide, we saw that B over 2TF is equal to 5.60. And remember, BF over TTF is equal to 5.60. I should mention that. If you look on the table again, sometimes people are often confused when they see this for the first time, because they say, wait, there's not an over 2 in the on the table B on table B 4.1b. And this is true, but that's because the B that they're defining on the table is for only half of the flange width. You have to look very carefully at how they're defining that B. This formula here takes into account the entire flange width. But anyway, this is 5.60, and this is clearly less than 9.15. Therefore, our B over 2TF is less than 0.38 over square root of E over Fy. Therefore, flange is compact. Our flange is compact. Then our web. Well, let's see. I need to compare the ratio I had previously, my web ratio, to 3.76 over square root of E over Fy. 3.76 over the square root of E over Fy. And of course, this is 3.76 over the square root of 29,000 over 50. And this comes to 90.6. 90.6, and again, this is coming from the same table. 90.6, and we compare this to our limiting web ratio, H over TW, the height of the web over the thickness of the web, and that is equal to 41.2, and this is clearly less than 90.6. Therefore, our web is also compact. Now, since both our web and our flange are compact, therefore chapter or section F2 applies. Therefore, chapter F2 applies. So we can use all of the equations that we've been used to. If one of these was not compact, or one of them was slender, etc., we would have to use one of the later sections. So chapter F2 applies. Again, we start our flexural analysis by first determining which section of the code to use. And we do that by determining the the compact section criteria or ratios. I'm going to pop out periodically and save this file just in case of crashes or anything of the sort. And I'm always paranoid, making sure we're still running, etc., etc. Okay, so now that we know we indeed have a compact flange and a compact web, our next step is actually going to be to calculate CB. I can't recall if I've actually calculated CB in an example for you, so I want to just do that here. So 3, calculate CB. And CB is found at the very start of chapter F. It's found at the very note, the beginning note for chapter F. Again, just equation F1-1, I believe. Let me go there. I'll give you a page number. Oh, let's see, where did that go? Chapter F, I'm trying through my manual. Yes, that is equation F1-1. That is the one we'll be applying. Now, if we remember from class, the CB criteria is based on moment distribution. But in order to do that, I'm first going to need to actually have the moment. Or in other words, I need to find the moment as a function of x. Alright, so, you know what? I don't know if I necessarily need to work all the way through this. But if you have a... you could do this two ways. You could either get the moment function, or you could get a... or you could do a shear and bending moment diagram, whatever technique from statics or mechanics of materials you wish to use to find your moment. So we have a free body diagram like this. We have a 500 kip foot moment here, and a vertical force of 20 kips here. Now, what I did was I went through and actually used the method of sections to find the moment function. And what I got was, I did also the shear function, it's just constant across. But our moment function here will come to m as a function of x is equal to 20x minus 500. If you need to review how to do this, please see your statics book or check some of my older lectures from mechanics and materials that are posted to the site. Now, from this, I'll need to so I have my moment function. This gives the moment in kip feet as a function of x in feet. So next, I'm going to need. This is all based upon quarter points. In other words, quarter, quarter, quarter. The quarter points along the beam. So my quarter points are going to be found at particular x values. So I want to find those. Well, they're going to be at x equals. Well, let's see. L over 4, L over 2, and 3L over 4. If you're trying to look into the manual and see where I'm getting these 3L over 4, you will not find them anywhere. All I'm really doing is applying some common sense, geometry, and the definition of quarter points. So for this beam, since our beam is 25 feet long, this means that we're really looking for the moment at 25 over 4, 25 over 2, and 3 times 25 over 4. Or simply 6.25 feet, 12.5 feet, and 18.75 feet. Now, our M max is going to occur at the left end, and it is 500 kip feet. Now, NA is going to be the M at, if I'm going to take the 6.25 foot value and feed it into the m of x function. This is m of 6.25 feet, and this is 375 kip feet. MB is going to be m at the middle, which is m at 12.5 feet. Again, I am not multiplying m by 12.5 feet, this is a function notation. M at 12.5 feet, and that comes, oh, that's a negative, and that comes to negative 250 kip feet. And finally, MC is equal to m times 18.75 feet, or sorry, not times, I'm doing it myself, m of 18.75 feet, and this will come to negative 125 feet. However, if we look on the note carefully for the CB calculation, we're supposed to use the absolute value. So this will be 375, this will be 250, and this will be 125. So finally, CB is equal to 12.5 m max. Again, this is equation F1-1. If you don't know how to find equations in the steel manual, please come see me during my office hours. You do need to be able to find equations by equation number quite readily in the steel manual. And you should be getting in the habit right now of tabbing your manual if you haven't already started. 2.5 m max plus 3 ma plus 4 mb plus 3 mc. Now, if you plug all those numbers in, let's see, we get 12.5 times 500 over 2.5 times 500 plus 3 times 375 plus 4 times 250 plus 3 times 125. And if you look closely on that note, you'll see why I mentioned at the beginning in the prompt that this was braced at the far end. If this thing wasn't braced, CB would automatically, for a cantilever, and only for a cantilever, it would automatically equal 1.0. But in this case, if you plug all those numbers together, you will get that CB is equal to 1.667, assuming I didn't flub the numbers up. So 1 2/3 for our CB. So we have our CB value. So you can see here why assuming 1.0 is so conservative. Yes, it's not going to hurt you in the sense that you're not going to design something that will fail, but this is something that substantially adds to our moment capacity. The CB is usually multiplied. Sorry, if you look at the next equation, say like F2-4 or F2-2, you see that we're directly multiplying a calculation by CB. So this CB will end up increasing the moment capacity that we would otherwise get by 67%. If we were conservative, and if we were overly conservative and assume that CB is just equal to 1.0, yes, we would be saving ourselves a little bit of time, but we would really be hurting ourselves in terms of capacity. We would most likely end up using a section much heavier than we would otherwise need. Alright, so now here comes the fun part. Nope, don't want that. Here comes the really fun part. Alright, so what I need to do next is, my next step is going to be to calculate the LP and LR. I need to know what range I'm in. I need to know where in the lateral torsional buckling regime I'm at, just like as we talked about in class. And I need to compare my brace length to my LP and LR to find what ultimate equation I'm going to use to determine my overall moment capacity. So my fourth step is to calculate LP and LR. Now LP is the easy one. Well, actually, I should say to determine which LTB region we are in. Okay. Now, let's say, so first of all, I'm going to get my LP. That one's fairly straightforward. Sometimes you'll get lucky and you'll actually be less than this, and then you can just stop and you don't have to do the really hard work. The LR, that's the one that's obviously the beast. So LP here, this is again equation, F2-5, and LP is going to be equal to 1.76 times this RY times the square root of E over Fy. And this comes to 1.76 times 1.81 inches, our weak axis moment of inertia, times the square root of 29,000 over 50, and this then comes to 76.7 inches, or 6.39 feet. So no dice, we are clearly beyond the plastic range, the plastic limit state. So we got to see where else we are. The other question now becomes, we're definitely beyond LP. The question now is whether we're between LP and LR or whether we're beyond LR. So I got to go through the whole LR calculation. Joy. So LR, if we look on equation F2-6, so let me label this, annotate this as F2-5. Then equation F2-6 will be, well, LR, as you've seen before, is 1.95 RTS times E over 0.7 Fy times this horrific double square root of JC over SXHO plus the other square root. And when I do the math on this, I am not even going to try to do this all at once. I'm going to simplify my computations by dividing this into, by taking this in chunks, basically. And you'll see what I mean by that. JC over SXH0 quantity squared plus 6.76 times 0.7 Fy over E. Fy over E quantity squared, as we get from the manual. Okay, 0.7, 6.76, JC, 6 over HO. Yes, okay. So what I'm going to do is I'm going to simplify this. I don't want to try to throw this whole monster into my calculator all at once, so I'm actually just going to take this in bite-sized chunks. So I'm going to get this part first. Well, JC, J times C over SXHO, this is going to be, these are all just things from the table, from the original section properties, 3.02 inches to the fourth times C. Now, if you look on page 16.1-48, you'll see that for W, and look at note F2-8A, you'll see that so F2-8A, C can be equal to 1.0 for I shapes, for doubly symmetric I shapes. And so we have that in this case, so we can use a C of 1.0. SX are for our strong axis, our S for our strong axis again, It's just something we had from our table earlier. And this is going to be 151 inches to the third, and then times h naught, which is going to be 20.5 inches. 20.5 inches. And if you throw all that in the calculator, this entire ratio will come to 9.76 times 10 to the negative 4. So I'm not even going to try to get this whole thing all at once. That's just too messy. I don't like messing with it. Okay. So the next chunk that I'm going to get is going to be the just this part here, the 6.76 times 0.7, etc., etc. The 6.76 times 0.7 Fy over E quantity squared. Well, this is 6.76 times 0.7 times 50 over 29,000. Quantity squared, and this comes to 9.84 times 10 to the negative 6. So now I have this part, and this part. What I'm going to get next is I'm going to get this entire inner root. So I'm only going to calculate the inner root next. Inner root using the previously calculated chunk values. So I'm going to simply have the square root of JC over all that, and that's this number here. It's going to be 9.76 times 10 to the negative 4 quantity squared plus 9.84 times 10 to the negative 6 here. 9.84 times 10 to the negative 6. And so my inner root is going to come to 0.003286 here. Next, what I call the outer root is, I don't need to square this one because this thing already has the square on it. But this one did not have a square, so that's why I squared it here. Then my outer root, which is basically everything under this root, and I'm just turning this into a decimal now. My outer root, so you can sort of see my strategy. If I have a big, ugly equation like this, I'm just gonna break it down and take it in bite-sized chunks. Square root of 9.76 times 10 to the negative 4 plus my 0.003286 from the previous step, and this comes to 0.0653. And then finally I can calculate the overall here. This has now all been reduced to a single decimal point, so the rest is not too bad. LR then is just equal to 1.95 times 2.19 inches times 29,000 over 0.7 times 50 times our 0.0653. And I get this comes to 230.9 inches or 19.2 feet. So LR is equal to 19.2 feet, but our LB is equal to 25 feet. So therefore we are now in the far lateral torsional buckling range, and so we are, equation F2-3 is going to apply. So that's what we're going to actually use to determine. So again, this is less than our braced length, so therefore equation F2-3 applies. Equation F2-3 applies. And you could probably guess what the next step is. The next step will be actually applying that equation. So each time I'll just, each step I like to just go back and save, make sure we're still rolling, etc. Okay, finally, our last step is to actually calculate the phi mn. Calculate phi mn. So 5, calculate phi mn. Are basically our overall moment capacity, our design moment capacity, and we're going to compare this to our ultimate moment. Now, if we look at equation F2-3, we find that it's based around calculating nominal moment capacity first, so we'll do that. Mn is equal to F critical, or FCR, not critical, but FCR, FCR Sx, and this has to be less than or equal to MP. Again, when you see this kind of less than or equal to sign in the SEAL manual, what it is referring to is that you're going to do this check, but you're not going to you're going to use this value, but you're not going to let it go ever go any larger than the MP value. So I need to know my upper limit first. So let's first get that MP. MP, and again, this is equation F2-3. I'm trying to annotate my equations as I go. F2-3. MP here is going to be just my Fy Zx. So that's 50 KSI times the Zx that we got from our table, which is 172 inches to the third power. And this comes to 8,600 kip inches. 8,600 kip inches. So our whatever we get for this cannot exceed this. And if it does exceed this, it doesn't mean that we've done something wrong. All it means is that something the math doesn't quite work out here, and we can't for a variety of reasons. And we can't ever go beyond this. So if you ever get that this is larger than this, you just take this as your nominal moment capacity, even though you're in the greater than LR range. Okay. So Sx is obviously trivial, but we need to find our FCR. That's going to be another lovely equation, and that is equation F2-4. And for this, I'm also going to simply use the strategy of breaking it into pieces. F2-4, well, FCR is equal to CB, so here's where the CB comes in that we calculated earlier, pi squared E times LB over RTS quantity squared times the square root of 1 plus 0.078 times JC over SXHO. Now, notice we already calculated this ratio earlier, so I'm not going to have to do that twice. Times LB over RTS quantity squared. Ah, that's another, see this ratio? I see this ratio twice. So what that tells me is that what pops out to me with that is that I want to calculate this separately, just to make my math a little bit simpler. So that's actually the very first thing I'm going to calculate. My LB over RTS squared, this is going to be 25 feet. However, I need to be very careful to use consistent units. So I'm going to multiply by 12 inches per foot. 12 inches, that looks like a pi. 12 inches per foot, I suppose. all over the RTS from the first tail, which is just 2.19 inches. And all of this squared, and we get that this ratio, or this square, this term, whatever you want to call this stupid thing, is 18,765.2. Then our, I'll also list our JC over SXHO. And this is from, we saw this earlier, we don't need to recalculate it, it's the same stuff as on the previous step. And this is just 9.76 times 10 to the negative 4. 9.76 times 10 to the negative 4. Then, let's see, the rest is just sort of working through it. I won't do the inner or outer root thing here. I don't think there's a lot of benefit for that this time. So, let's see here. Let me double check something in my numbers on my calculator really quick here. I want to make sure I got something. Yeah, we're good. I believe so. Let me double check my numbers here. 666 times pi squared times 29,000 over. Just a second, I'm just checking one of my numbers in my calculator. Oh. Interesting. It seems I may have actually made an error in one of my calculations. Something seemed a little bit low in the numbers that I had written up. So forgive me for a moment. I don't want to stop recording because this thing generally records in one take. So give me a second. I'm going to fix some numbers that I got earlier. I already worked through these calculations in advance, but apparently I made a slight math error, as can happen from time to time. So give me just a minute. This won't take that long. Just for me to fix this here. And that might actually dramatically change the result. 25.4 here times 1 plus 1.428 comes to 39. That changes everything. 39. I was wondering why it was so low previously. 61 KSI. 39.61. Just a second, I'm just letting the numbers cascade through. 5981. I have another sheet of notes that I'm keeping for my own purposes. Let's see. Let's see, 5981 times 0.9. So to err is human. Times 0.9. 4844 or 5, I guess. Sorry to leave you hanging here, but just give me a minute. And 403. So that makes me feel a lot better. You'll see why. Okay, anyway, let's continue. Sorry about that. Sorry for that little intermission. Now, let's see. So I'm going to calculate this. I'm just going to throw all the numbers in. And I'm going to have 1.667 times pi squared times my pi squared times pi squared times 29,000 over my 18,700 and where'd that go? 65.2. times the square root of 1 plus point 0.078 times 9.76 times 10 to the negative 4 times this quotient here, which is again our 18,765.2. Alright, so when I work through this, I find that all this nonsense is then equal to 25.4 KSI. It's KSI because this is dimensionless, this is dimensionless, this is KSI. And then times the square root of 1 plus 1.428. And that's also another advantage of breaking this into chunks. I didn't need to recalculate this part here. I was comfortable with this. But when I found an error in this part of the expression here, so I don't have to go and recalculate everything. Just do some math, but not everything all over. Quick enough that I can do it without stopping the tape. Well, it sounds digital, but whatever. This comes to, and when this is all said and done, I get that F critical, or FCR, is 39.61. I shouldn't probably call it F critical. I have to review what CR stands for, but anyway, FCR is going to be 39.61 KSI. So we have that, and then MN is going to be equal to FCR SX, which is equal to 39.61 KSI times SX, which is 151 inches to the third power. Inches to the third power, and this is going to come to 5,981 kip inches. And I can compare this to MP. This is indeed less than the 8,600 we got previously for the MP. So indeed, our FCR SX is indeed less than or equal to MP here. So then our nominal moment capacity is simply going to be 5,981 kip inches. Let me continue on to the next slide. So now we have our nominal moment capacity, 5,981 kip inches. So this means that our phi mn is equal to 0.9 times that, 5,981 kip inches, which equals then 4,845 kip inches, or simply 404 kip feet. And this is our ultimate moment capacity. The way this section is braced, the way this section is designed, the material it's made of, basically everything about this beam, what it's made of, the A992 steel, the unbraced length, and the cross section, all combined together in all the wonderful equations that we have seen to produce a phi mn of 404 kip feet. And 404 kip feet is less than 500 kip feet. Therefore, phi mn is less than M ultimate. Therefore, this thing fails. We need 500 kip feet of capacity. We only have 404. This is not going to be adequate. Beam fails, redesign. So if this was a design problem, I would go back and select a heavier section and then recheck it again. Although this is one area for design, if you do have to run through the if we're doing design, you can use beam tables and things like that, or the design aids, and the other things we discussed in class. If you're doing something, say, with built-up members, or something that you can't use those design aids, if you're doing a lot of calculation and recalculation, what you would probably want to do is you would want to take these equations and put them into, say, like a MathCAD or an SMath spreadsheet, or maybe even a Excel spreadsheet, something like that. Alright, that'll do it for this evening. It's getting kind of late, I believe. So, man, I'm doing videos at 10:30 at night. Lovely. But anyway, I just wanted to take the time to go through and do a long-form example, so hopefully that clears up how to handle calculations for lateral torsional buckling. I'll see you all in class later on Monday, and I'll see some of you tomorrow. But anyway, that should do it for now. And as always, thank you for watching.